All right, so we've been talking about the sequences. Sequence is a list of numbers separated by commas, and ultimately we want to recognize a pattern between consecutive numbers, or if we use the recursive idea, maybe just basically using successive terms or previous terms to find the next one. Now, a sequence doesn't have to be that way. A sequence can just be a list of numbers, and there'd be no real relationship between them. Okay, but we'd like to investigate the ones that have patterns. Okay, a series is using the same sequences. I said series, so she answered. Shut up. So series are the same thing as sequences, but you take the comma out and you either put plus signs in or you put minus signs in. Okay, and we're going to specifically deal with adding them. Okay, but a series is taking the indicated sequence and adding the terms together. Okay, there's two types of sequences that let me rephrase that. There are two types of series that we want to talk about. And then when I say series, it relates back to the sequence as well. But there's what we call a finite series. Okay? If something is finite, it means you can count it. It means every single object in the list can be provided with a number. Okay? So, would you guys agree that there is a lot of grass blades out in the courtyard? Yes, but is there an infinite number? No. Okay. Every one of them can be clipped, and you can put a number to it, and you go on to the next one, right? There is a finite number of grass blades out in the courtyard. Okay. The number of digits to pi. Can you do that? No. Okay. The digits to pi are infinite. Okay. So there's a difference between finite and infinite. Infinite goes on forever. You cannot count how many you have. Okay. Finite, you can't. We need to be able to realize that when we want to talk about series, okay? Because some series are finite. There's a starting value and there's an ending value. Okay, when we go out and look at and count the grass blades out there, there is a first grass blade and there's a last grass blade. Does that make sense? Okay. Huh? No. When we get past 20, you're going to be stuck. All right. So, we're going to talk about two types of series, the finite ones and infinite ones, okay? So that's one thing that we have to pay attention to as we go through these scenarios, okay? Here are just some examples, okay? Here's the sequence that we talked about 3 days ago. This is a arithmetic sequence, okay? Adding 3 to each, okay? And we see the way... Because a lot of times they won't say this is a finite sequence. It's the notation. There's nothing coming after this 18, okay, that tells us there should be a 21 or a 24. Does that make sense? If I look at this one, this is an infinite sequence because of these, what do you guys call these in English? Ellipses. Those ellipses tell us that this pattern, the pattern that is established there, is going to continue without end. Okay? Now, we could also see something like this. If I go 3, 6, 9, 12, okay, and then I get to like 21, 24, okay, or I could just say finish at 21, okay. I've established a pattern. That pattern is going to continue through these ellipses. So there's some values there that will add in there, but then 21 finishes it. So that would be a finite sequence. Okay. So how does a finite sequence relate to a finite series? We took the commas out and we put plus signs in. Okay. Same way with the infinite series. Okay. Does that make sense, everybody? All right. Says an arithmetic series is a series whose terms form an arithmetic sequence. When a series has a finite number of terms, you can use the following formula to evaluate the sum. So first thing we have to do is realize, does our sequence follow, or sorry, does our series, if we look at just the terms, does it follow a sequence pattern that is arithmetic? Is there a common difference between successive terms? If it does, and if it's finite, we can use this formula here. Okay, we can use this formula here to come up with the sum of all of those terms. Okay? So, the way we do this, we say S sub n. Okay? Sometimes this might be referred to as a partial sum, because we can, even if we have an infinite series, we can say, okay, let's look at the first 10 terms and just chunk that out. Delete everything else after that first 10 terms. And now we have basically a subsection of our series that is now finite. Does that make sense? But if I added those up and found that sum, that would be a partial sum of the entire sum. Okay, so we'll talk about that stuff as we move on. So you might see the word partial sum, but we're going to use the same formula here. Basically what you do is you're going to, so when it says S sub n, n is the number of terms that you're adding together. Okay, so that's how many terms are in the sequence. Okay, we're going to take n divided by 2. N, again, is the number of terms that we have. We'll divide it by 2, and then we're going to multiply that by the sum of the first term and the last term. Okay. If we have a little bit of time tomorrow, maybe we'll go through the proof of why this formula works. Okay. But a sub 1 is the first term, a sub n is the last term, n is the number of terms you're adding together. Okay. So let's just do something real quick here. You guys take a moment on your own, without the formula, add those together. Figure out what that sum is. Add them together. Did you get 110? All right. So, if you were to take your calculator and plug these numbers in, you get 110. Okay? You guys? All right. So let's see this formula. So we know one route of getting that 110 by adding. Okay? Let's see this formula that says S sub n, which is equal to n over 2 times a1 plus a sub n. Let's see if that generates the same 110. Okay? Now, the only thing I have to know here is how many objects are in my series. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And we can maybe find that a different way here in a little bit. And now a1 is 2, and an is 20, right? What's 10 over 2? 5. What's 20 plus 2? 22. What's 5 times 22? Why would you guess that? Why don't you just know it? 20 times 5 is 100, right? 2 times 5 is 10, so we can add those together, 110. Okay. Now, let me ask you this. Let's say, so this list wasn't too bad for us to count, right? Count that there's 10 things there. Okay. But we know it's arithmetic. Let's say if this was like out to let's do this. I got Excel open here, so let's actually do a problem here. Let's say that we have 1,114. Okay. So what I've got here is a series that starts at 2, 4, 6, 8, 10. It's arithmetic, and it goes out to 1,114. And I want you to add all those up. But do we know what the numbers are in between 20 and 1,114? We know what they look like, but we don't know what they are at the moment, right? We have to actually write them down. Okay, so think about what the formula says. The formula says S sub n is equal to n over 2 times A1 plus AN, right? I don't know how many numbers are in this list. There's at least 11, but I don't know how many are in these ellipses here, right? Okay. But A1 is 2, and AN is 1,114, right? Let's see if we can find n. And we find n by knowing that this is arithmetic. You guys remember an arithmetic sequence, A sub n is equal to the first term plus n minus 1 times d, right? Okay. So let's do this. Let's say, so A sub n is a specific term in this list. Let's use that term right there. Because if I can put A sub n right there, I can put A sub 1, which is 2, right there. N minus 1 times d, what's the common difference here? 2, right? If I can solve for n, that's going to tell me the position that what number is in. Does that make sense? And that would then tell me how many numbers are in this list. So if I go ahead, I'm going to subtract. Actually, when I do this, it's going to be, what, 2 plus 2n minus 2. When I distribute that 2, 2 is going to cancel out, right? So what's 1,114 divided by 2? Say again? 557. Okay? So right now, so if I do this, that's the 557th term. So if I do this, 557 over 2 times this number here. Okay, so let's see what that ends up being. 557 divided by 2 times 2 plus 1114 gives me 310806. Okay, so that's what that's going to add up to. Okay, now if I go back to Excel, Excel is going to show me some of this. You do see, if I zoom in on that it is the 557th term, right? Okay, now the formula that I had in Excel right here was adding everything that was in this column. Is that the same number that we got using the formula? Does that make sense? So we didn't know, as we did this, we did not know all of these numbers that I'm highlighting. And you can kind of think about how big of a pain in the butt that would have been to find all those numbers that I just highlighted there. Okay, and to write them down and then to add them. If my goal is just to find what the sum is and not really worry about what these individual terms are, this formula allows me to do it. And we've got some other formulas at our disposal from previous sections that might provide some valuable information in completing this formula. Is it okay? What I want you guys to do, so this next one is just that. It's a little bit shorter, okay? See if we can use the procedure just went through to find the sum of this arithmetic sequence. Okay, so I'll give you a couple minutes to work on that. We don't necessarily have to add the entire series together. If we just want the first 3 terms, then A sub 1 would be 7, and A sub n would be the 15. Does that make sense? Okay, and you can just chunk that, see, and that's why it's called a partial sum, because we don't have to have the whole thing. We just have to have the one term we're going to start with and the one term we're going to end with. Is that okay with everybody? Okay. Now I don't know n. I don't know how many terms there are between 7 and 233. So that's where we want to use the formula A sub n is equal to a sub 1 plus then n minus 1 times d. A sub n, that is the term that is in this nth spot. And if I can find the nth spot, that's the number of terms that I have. So that would be the n here. So that's 233 is equal to a1, which is 7, plus n minus 1 d, and d is 4. So working through that, I get 233 is equal to 7 plus 4n minus 4. Add 4 to the 7. Oh, sorry. No. 7 minus 4. What's 7 minus 4? 3. I'll move that 3 over. This gives me 230 is equal to 4n. Is that okay? How many times does 4 go into 23? 5 times. Okay. So does this give me, doesn't work out real nice, does it? Make a mistake. It gives me 57.5 is equal to n, and that's not possible. Let's backtrack and see what happened here. All right, so this is my fault. I apologize. So that worked out to be, we can't understand. We got n to be, and this is what Maya was asking. She said, does the result come out to be a decimal? Well, we got a decimal. N is a position, right? You cannot be, you can either be the 57th term or you can be the 58th term. You cannot be the 57.5 term. That does not exist, right? Okay. So using Excel there, what I found was, I got a typo here. This is 235 is the number we want there. So I apologize for that. Okay. So if we go through with 235, so again, what is the position of that 235? So I put 235 here. I'll put the first number 7 there, plus then n minus 1 times our common difference. So now I get 235 is equal to 7 plus 4n minus 4. That's 235 is equal to 4n plus 3. So now I get 232 is equal to 4n. Now how many times does 4 go into 23? How many times does 4 divide into 23? 5 times. You'd be left with 32 then, right? How many times does 4 go into 32? 8. So what that means is that this 235th or 235 is the 58th term. Okay, so that whole process tells me what number that thing is in the list. So and that's the n right here. So I go 58 over 2 times 7 plus 233. So that gives me, so 58 over 2, what's 58 over 2? 29. And then 7 plus 233 is 240, right? So I'm looking at 29 times 240, and that gives me that value there. Okay, so that's the sum of those first 58 terms. Now, if I use Excel, okay, you see here, if I zoom in on this, we do see that 235 is the 58th term. Okay, now if I go up and I ask this to add all these together, it's because did I not delete everything out of there? Yep. If I add them all together, let me just do it this way because I got some stuff in here that's missing. So 7, 11, 15. Take that all the way through to 58 terms. Okay, we get that 235. So now I'm going to say equals the sum of everything in that column. Why is it not giving me? We're having an issue here. So this is the 58th term. 232 divided by 4, 58. Oh, I'm an idiot again. Well, this was 235. That's what that number was, right? So right here, it's 235. Okay, so now we've got, so no, it's not. So it's now 29 times this here, which is 242, right? So multiply that by 242. And we get, there's the 7,018 that Excel was showing. Okay, so my apologies in messing that problem up. We're going to do one more. All right, so what's the common difference here? Common difference is 5. So if I want to find what term 134 is, I'm going to go 134 is equal to the first term plus then n minus 1 times our common difference, right? That gives me 135 is 4 plus 5n minus 5. Okay. So that is 135 is equal to 5n minus 1. Okay. Why am I doing that? Goodness. Sorry. All right. So it's that last term, 134. Okay, so now when I do this, I'm going to add 1. So it gives me 135. That's where I was getting the 135 earlier. Okay, I was thinking ahead. So now if I divide by 5, what's 135 divided by 5? How many times does 5 go into 13? 2, and it leaves you with 35 over, or left over, right? Okay, so n is 27. So that means this is the 27th term. So then if I go 27 over 2 times 4 plus 134, okay? And the one thing you got to realize here is that this will all, if we do this correctly, if it's arithmetic sequence, this will all, if this is over 2, okay, and this is an odd number over 2, this has to be an even number here, okay, because our sum will always be a whole number. So we get, what, 138 times 27 over 2? Which is, you guys get 1863? Okay. There's an assignment 9-4. Okay, I apologize for the typos that I continuously put in here today. If we have any issues on this, let me know tomorrow. We talk about it again tomorrow. Have a great rest of the day.